Hi everybody, Physics Ninja here. Today I want to look at two variations of a problem that involves calculating the electric field produced by a linear charge density that's arranged in a semicircle. All right, in both cases, I'm going to assume that the total charge on this semicircular ring is a 12 microcoulomb. Now, the only difference between the two cases that I want to look at, so the case number one is I'm going to assume that this 12 microcoulomb is spread out evenly, okay? So that means that my charge density is uniform or constant. Same amount of charge in every little bit of this semicircular ring. Okay. In the second case, what I want to do is I want to put more charge in certain parts of the ring over other parts of the ring, right? So in that case, it's not uniform. So the way I'm going to represent that is going to be through this function. The charge density will be some constant multiplied by cos of the angle theta. And the angle theta is defined here. So what does that mean? That means I actually, for case number two, I have more charge that is closer to this center of the ring. And as I go toward the outside, up here and down here, that's where the angle theta is 90 degrees or minus 90 degrees. In that case, there's very little charge or no charge if it's 90 degrees. Okay, so we're going to show you how you can use symmetry to simplify the problem. And then we're going to integrate in order to calculate the electric field for both cases. Like with all my videos, if you like it, give it a thumbs up. Consider subscribing to my channel. It's the best way to support what I do. All right, let's get started. All right, first thing I want to do is just look at both of these cases again. Case number one, I have a uniform charge density. So that means if you look at any bit of segment, the total charge is uniformly distributed evenly on this ring. Okay, so it's kind of this 12 microcoulomb spread out evenly, right? Because I have just a constant charge density. In the second case, I have something that depends on the angle. And again, the angle here is defined here relative to this horizontal line, okay? This is the angle theta. Now, what that means, now, if the angle theta is 0, I get a maximum charge density. So there's more charge here than there is down over here. Right here, the angle is 90, so there is no charge. So that means that it's kind of more spread out, and then they become more evenly spaced as I get toward the end. Now, the other important thing is they are symmetric, right? Both of these charge distributions have to be symmetric. So that means that if you look at a little bit of segment over on this side at some angle theta, it has to have the same amount of charge on the other side because cos is a symmetric function. And that is also clearly the case for the uniform charge distribution. So my first step now is to calculate what is this this constant lambda 0 for both cases, because we also know that they have the same number of total charge. It's 12 microcoulomb for both cases. So let's calculate this lambda 0 first, and then we're going to calculate the electric field. All right, this charge density, remember, is simply the amount of charge you have per unit length. I'm going to call the length here S. Okay, so this is a small segment ds that goes along this circle. Okay, you could use dl also. It doesn't matter what the letter is. What you want to do now is if I wanted to calculate the total charge, well, first I just bring this on the other side. Okay, and now I would have to integrate both sides in order to get the total charge. Right? If I add up all of the small dq's, I get the total charge. And this quantity I know, it's 12. All right. Now, for both of these cases, I have to evaluate this integral. Okay. And we're going to show you how to do that for both cases. So for case number one, again, all you have to do is you substitute this charge density in here. So we have Q total is equal to, now we are going to think about this integral. The charge density now is just simply lambda 0. It's a constant. Now, what is this little bit of a length around this circumference? Okay, this is done using cylindrical coordinates, right? It's the radius multiplied by the little bit of angle that subtends over here going to this origin. And I'm going to integrate here from minus pi over 2 from minus 90 degrees all the way to 90 degrees because I'm integrating over this entire region over here. All right, now the next thing you do is you can factor out what the constants are from this integral. That's kind of important first step, simplifies the calculation. And all you're left now is you're going to be integrating from minus pi over 2 to pi over 2 of the angle. So you're simply adding up all of the angle here. So this is simply half a circle. The angle in half a circle then has to be 180 degrees or pi. Okay, so you're going to be left with lambda 0 pi times r has to be equal to the total charge for this case. So our lambda 0, I just isolate now that lambda 0 for this first case is the total charge divided by pi times r. Okay, so that is our first result, at least for the uniform case. Now let's go ahead and look at the case where the charge density is not uniform. All right, so in our second case here, what we have Q total, again, still 12 microcoulomb. The integral limits are going to be the same. I'm integrating from minus 90 degrees, minus pi over 2 to pi over 2. Now, my lambda now is different. My lambda now depends on the angle. So I have lambda 0 cosine of the angle theta. And again, a little bit of length of wire can be written as the radius multiplied by that angle. Okay, again, there are two constant terms, lambda 0 and r. You simply bring those in the front. Okay, so you have lambda 0 r, and then we're integrating minus pi over 2 to pi over 2 of cos theta d theta. The integral of cosine is sine. Okay, so that kind of simplifies our calculation. So at the end, my last bit of calculation that I have to do is simply lambda 0 r sine of theta and evaluated between both of these limits. The nice thing about this one, sine of 90 is 1. Sine of minus 90 is minus 1. So you end up simply getting 2 lambda 0 r for this result right here. Okay, so that means that my lambda 0, let me just write it out here. I'm running out of space here. Now it looks kind of similar. You got to be a little bit careful though. There are some important differences. It's the total charge, and in this case, it's divided by twice the radius. Okay, let's go ahead and highlight that. That'll be an important result that we're going to use when we calculate the total electric field. Okay, so we have both our lambda 0 constants. Now we're going to go on the next page and we're going to consider the electric field in each case produced by both of these cases. All right, we're first going to look at the uniform charge distribution here. And the first thing I want to do is let's consider a little bit of charge here. Call this little bit of charge dq. It's a certain distance r away from that origin. Now if I draw a line linking that charge to the origin, it is going to point in this direction. This is going to be the electric field produced by this little bit of charge dq. Now that angle theta here is this one over here. And that has to be the same angle as this one right here. Okay. Now, how do we write dq? Well, dq, the little bit of charge is simply the charge density, lambda 0, multiplied by the length of that segment, which I've called ds. So it's lambda 0, and the little bit of length here is going to be r d theta. Okay, that's the amount of charge here that I'm considering. Now, how would you write down the magnitude of this electric field here, which I'm going to call dE? How would you write down just the magnitude of it, right? What's the length of that vector? So again, it's just the electric field produced by a little bit of charge. So I write it as K. And again, K is just a constant, which is 1 over 4 pi epsilon 0. K, the amount of charge is dq, and divided by the distance squared, right? The distance now is simply the radius squared. Now I'm going to eliminate this dq, so it's going to be the constant k. And dq, I simply substitute all these terms here. These are just constants. R d theta and over r squared. Now you can simplify this expression a little bit. I can cancel out an r here and this one here, and I can clean this up a little bit. So at the end, the magnitude of the electric field produced by one little segment, dq, is k lambda 0 d theta over r. Okay, now I'm not done, because now I have to integrate, right? I have to integrate all of the angles. However, before I do that, we want to use symmetry now, okay? And what I mean by that is we just considered this little bit of charge, but every time there's a charge at the top of this semicircle, there's an equal charge down here at the bottom. Now, if you think about the electric field produced by this little bit of charge, it's going to point like this in this direction. It's going to have the exact same magnitude. Right? Both of these have to have this magnitude because it's the same distance away from that origin. So guess what? When you add the green vector to the orange vector, guess what you're going to get? You're going to get a total electric field that simply points in this direction. Okay, all right, at the end of the day, my total electric field has to only be in this X direction because the vertical components are always going to cancel with each other, but all the horizontal components are going to add to each other. So how do you write down the horizontal component of just this little bit of vector? So all we're doing here is just grabbing the horizontal component, which means I would just call it like this. The little bit of horizontal field, right, is simply going to be dE. And I'm just going to drop the absolute values here. I'm only talking about the magnitude multiplied by cosine of theta. Okay, and this is the expression that I want to integrate. So you substitute everything in here. K, lambda 0, r. We have cosine of theta and d theta. And to get the total electric field now, what you do is you have to integrate. You have to add up all of these little bit of components that I'm going to add in the same direction. And I'm integrating over the angle theta. So that's from minus 90 degrees to plus 90 degrees. And this is going to give me my total electric field, which is going to be in the X direction. Okay, so we have to evaluate this integral. This is pretty straightforward. So the total electric field in this X direction here, take out all the constants from the integral. So that's K, lambda 0 divided by the radius. And you're left with integrating, something we've just done. We're done integrating cos theta d theta. Right? We just said the integral of cos theta is sine and evaluated between pi over 2 and minus pi over 2. And that gives you, well, let's go ahead and do it. So we have K, lambda 0 over r. This is sine of theta. And this is pi over 2 minus pi over 2. You substitute our limits here. K lambda 0 r. This becomes sine of pi over 2 minus sine of minus pi over 2. All right, each one of these guys, well, this guy here is 1. Let's put that in a different color here just so it sticks out. Minus, and this becomes minus 1. All right, so here you get just the number 2 that comes out in the front. So you put the number 2 here. You have K lambda 0 divided by r is my total electric field. And just to get the direction right, I'll just put an I hat vector here. But I know it's in the positive X direction from the symmetry. So let's just go ahead and clean that up. The last thing I can do now is I can go ahead and I can substitute what is my lambda 0, okay? If you substitute lambda 0 over here, you're going to get that your final expression for the uniform case, okay, is going to look something like this. So I have 2k divided by r. Now the lambda 0, I'm going to substitute this. It's the total charge of the ring, or this half ring, and divided by pi r squared. I'll put the pi in the front and put the other r over here. So at the end, this is what you get. Okay, and again, it's in the x hat direction. So that is the result here for my total electric field for the uniform case. Now again, you could go ahead and substitute what this value of K is and just write it a little bit differently, but I think this is fine for now. Now let's go ahead and do the other case, which has a non-uniform charge distribution. See how it compares. All right, so I left kind of the diagram the same for this case, but all the symmetry arguments are all going to be the same, okay? Because the only thing that's going to change is that these vectors are now all going to have different lengths, but every time there's a little bit of charge here, there's an equal amount of charge on the other side. And the only thing that's different is if I consider charge where the angle is 0, then I have slightly longer vectors. But when I'm going to add them all up, again, I have to have a total field in the x direction. So again, we're just going to start by writing the little bit amount of charge now. It depends on where you're located on this semicircular ring. So we're going to have the charge density, which is lambda 0 cosine of theta this time, and multiplied by a little bit of length, which is r d theta. So that's what clearly makes this problem a little bit different. Now we proceed again using the same formalism, right? We write down what is the magnitude of dE. Okay, I'll just write it as dE. I'll just skip the absolute values here. So again, it's the constant k. The amount of charge we have is lambda 0 cosine of theta r d theta, and divided by r squared. That's the distance to the origin. You can eliminate one of these r factors again. Now again, what I want to do now is I'm not interested. I have to use the symmetry again. So I really want only the x component of these fields. So that's simply dE multiplied by cosine of theta again. Now notice when I group both of those, if I substitute this expression here into the expression for dEx, what I end up getting here is k lambda 0. Look at here, I get a cos squared, okay? And that's what makes this problem a little bit different. And again, that's simply divided by the radius. So this is the little bit of field in the x direction produced by a little bit of charge dq. Now, all you have to do is add up all of these contributions, right? If I add them all up, and again, my limits are the same, minus pi over 2 to pi over 2. I'm going to get the total field. So the total field, again, has to be in the x direction, is going to be, take out all the constants. We have k, lambda 0 divided by r. Now you have to integrate this more complicated expression because it's a cosine squared theta d theta. Okay. The way that I typically do these guys over here, you want to do it kind of without a calculator. You could try to use a trigonometric identity. Okay, and one trigonometric identity for cos squared is 1/2 plus 1/2. Use the double angle identity. Okay, this you can look it up on the internet or look it up in your book. Okay, and this is a lot easier to integrate. All right, I went ahead and substituted in my trigonometric identity, and now all we're left to do is evaluate this integral. Not too difficult. All right, so we have k lambda 0 over r. Now the first term simply becomes theta over 2. Now the second term here becomes sine of 2 theta and over 4. Okay, and again, this whole term here has to be evaluated between both of these limits. Okay, now something is going to happen here when I substitute in my limits of integration here, because I'm going to get 2 times pi over 2. That's sine of 180 and sine of minus of 180. Well, remember, sine of 180 or sine of pi is equal to 0. Okay, likewise, doesn't matter if it's positive or negative. So this term here doesn't contribute anything to the integral. Okay, now we do have to worry about the other term. So this is going to be k lambda 0 over r. And this simply becomes, again, sorry, it's pi over 4, and then minus pi over 4 over 4. So at the end, you group all the terms together, we get k lambda 0. Add both of those, you get 2 pi over 4, pi over 2. Okay, so we get pi over 2r. All right, so that is my final expression now for the total electric field produced by this non-uniform charge distribution. Now, what you can do again is go ahead and substitute in what is the lambda 0. Okay, so let me go ahead and do that over here. So my substitution for lambda 0 is going to write it in terms of the total charge, right? So I get pi k. Lambda 0 was q total, and divided by 2r, this becomes 4r squared at the end of the day. Okay, so if you have a look at this expression, now let's go ahead and compare them one another, and let's just substitute in the numbers. If I assume that the radius of this semicircular ring is 0.2 meters, and I told you that the total charge was 12 microcoulomb, let's compare the numbers. All right, one thing I want to just point out here, so I have both results, the uniform charge distribution and the non-uniform case. Again, these are the results that we got in terms of some of the parameters, the total charge on each semicircular ring. Now, if you have a look in both cases, we have this kq over r squared. This one also a kq over r squared here. I forgot the direction here. But this looks like, right, this would be the field produced by a point charge located a distance r away with a magnitude equal to 12 microcoulomb. The geometry now has introduced this numerical factor in the front, right? We have 2 over pi for the uniform ring, and we have pi over 4 for the other ring, okay? That's kind of an interesting result. So now if we go ahead and we substitute our numbers, the k value is 8.99 10 to the 9. You substitute all of this, and for the uniform charge distribution, I got 1.72 times 10 to the 6, and that's measured in newtons per coulomb. And for the non-uniform charge distribution, I got something that's a little bit bigger, okay? 3 over 4 is a little bit bigger than 2 over 3, okay? And that just happens just because of the charge distribution right here, right? There's more charge in the front that's producing a bigger x component than the case with the uniform charge distribution. So intuitively, that kind of makes sense. I could have probably guessed that it was going to be bigger for this case. And substituting the numbers is 2.12 times 10 to the 6 newtons per coulomb. All right, so there you have it, folks. These are 2 cases to how to calculate the electric field. All right, hopefully you learned how to set up the equations and you learned something in this video. We'll see you next time.